Bismillahirrahmanirrahim. Assalamualaikum and good day. In this video, I'm going to explain the last topic of this course, which is the residual analysis and model checking. Okay, before this, we have go through the ANOVA. So actually, ANOVA has assumption, okay, which is the observation are normally distributed and IID with the same variance for each treatment. Okay, this means that we have a several level, okay, different level for each factor. So for each factor level for the observation, it should be normally distributed. IID here, independently distributed, means that each of the observation are independent for each other and they have the similar distribution, which is normal, and then the variance is also similar among the observation for each level. So we need to check whether this assumption has been fulfilled. So this can be conducted by checking the residual. So we have already come across residual in the previous video. Okay, so I just recall back some of the slide. Okay, so this is the residual actually. Okay, the random error, which is the difference of the each observation with their level average. Okay, so Yij is the each of the individual observation, and then the difference with the level average. Okay, and then we also can visualize for each observation. Okay, for example here Y11, which is equal to 2.1. Okay, what contribute to this value is actually is equal to mean overall. Okay, and then the ith level effect, which is in this example for the first level effect, and then the epsilon 1, so referring to the first observation error. Okay, so then we can visualize, which is, okay, the mean overall is 1.5 here. Okay, 1.5, and then the effect of the level and then the error, so we can obtain the observation, individual observation. In ANOVA, the error should be the measurement error, and it is the effect of the nonsense factor that are not considered in the experiment. So that is another assumption of the error. And then in order to make sure that the F ratio follow the F distribution with the control limit, given that we have already learned how to compute this one, okay, the control limit or the critical value in the hypothesis testing. So the error should satisfy the following criteria or the requirement. So it is normally distributed, independent, and then the mean is 0 and the variance is constant. Let's refer to this example. Okay, for the error, we compute by using this okay, residual, we call it, because now instead of mu I, we use the y bar I, so means we refer to the sample that we have. Okay, so this is the data. Okay, and then for each level of the factor, we have average. Okay, so there are 4 average because we have 4 different level of the hardwood concentration. So now for each data or observation, we compute the residual. Okay, so means that the observation minus the average of the level, okay, the respected level. So 7 minus 10, and then 8 minus 10, and so on. Okay, and then second level, 12 minus 15.67, okay, until we finish all the 24 observation. Okay, then we have the table of the residual. Okay, so if the observation is smaller than the average, so there is negative sign for the residual. So we are going to use this residual, okay, data in order to check the assumption. So it can be checked by using the plotting the normal probability paper. Okay, so we use this normal probability paper by plotting the residual. Okay, then we can determine whether it is normally distributed or not. And then we want to check the independency, okay, whether the residual is independent. So we can plot by from graph of residual against the time of run. Then we're going to check the zero mean. So if we use the equation of A1, so it is calculated just now. So if we calculate the residual by using the A1 equation, okay, which is this one, okay, then the zero mean assumption is already satisfied. And then lastly, we're going to check the constant variance. So this can be checked by plotting the residual against the level, and then we compare or we observe the spread of the residuals, and then we examine the range, which is the difference between the maximum and the minimum residual in the run. So this is the example of the plot, okay, by using the normal probability table. So once we have plot this, okay, we can define it by observe the point here, whether it can be said is distributed in a straight line. So if it is straight line, so we can conclude that the residual is close to normal distribution. So this one also can be done or carried out by using software. So we just check whether it is straight line. So how we are going to plot this one? Actually, there are several procedures that need to be undergo. So the first one, we rank the residual in ascending order. Okay, the smallest first and then the largest. And then we estimate the cumulative distribution function for the EK. Okay, so using this formula, okay, K is the order of each residual, okay, K equal to 1 until n. So because this one already ordered, so we denote as EK, okay, not the epsilon just now, because epsilon is in overall residual. But now once we have ordered the rank, so we denote it as EK. So K is the ranking of the residual, okay, K minus 0.5 divided by n, which is the number of observation, or in this case we want to compute in terms of the residual, so n is number of residual. And then once we have we have compute the PK and we have the EK, then we will use the normal probability paper to plot the pair observation or pair data of EK and PK. And then lastly, we make conclusion from what we can observe from the normal probability plot just now. Okay, so if it is straight line, then we can conclude that it is normally distributed. Okay, let's refer to the residual of this example just now. Okay, so now we take all this residual and then we rank it from smallest to largest. Okay, you can carry out it easily by using Excel, but I'm not going to demonstrate by using Excel. Okay, just I want to give you just an example. Okay, so the smallest value here, okay, is this one, right? Negative 3.67. Okay, this is the smallest. And then the largest is 5. Okay, positive. So we use this example, okay, 3.67 for the first rank of the ET just now, okay, E1, okay, for the smallest. Then we try to compute the PK. So this is the formula. Okay, for the first rank, E1 is equal to negative 3.67. And then N here is 24. Okay, the overall total of the number of the residual. So we compute the first P1. So K equal to 1. Okay, so this one is K, okay, for the first ranking, and then minus 0.5 divided by 24. Okay, then you can try to calculate, and then we put in a table for the pairs of EK and PK. So for the first rank just now is negative 3.67. So the respected PK is 0.0208. Okay, so this is for the first rank. And then until the last, okay, which is the largest residual, which is equal to 5. So for E24, okay, so K minus 0.5 divided by N. Okay, so K is 24 minus 0.5 divided by 24. So we get this value, okay, the last one, 0.9792. Okay, then once we get the pair of the EK and PK, so we plot the data, okay, by using the, sorry, not this one, okay, we use the normal probability paper. Okay, we can see that it should be increasing. Okay, so because we can observe also from this table, so the PK is increasing and also the EK also increasing. So it should have the straight line if it is normally distributed. Next, we're going to check the independent distribution of the residual. So we can plot for the EIJ versus the rank order. So we can examine whether there are systematic pattern. Okay, so if it is random, so it is independent. Systematic pattern means that if there is a increasing pattern, decreasing pattern, or like parabolic and so on. Okay, but for this example, we can see that it is random. Then we're going to check the next assumption, which is the zero mean. Okay, so we can use this formula. Okay, each of the observation we minus the average of its level and then divided by n. So we take this value difference for all the observation, and then the summation should be equal to 0. So why it should be 0? Because if we look at this scatter plot, for example, okay, so there is a negative and positive error. Okay, so if we sum up all the error, it should be 0 because negative value and positive value will be cancel out each other. So it is 0. Means that the value of positive and negative is approximately equal. So when we sum up, it cancel each other. Then we're going to check the constant variance. Okay, so this is the last assumption. So for this example of percentage of concentration just now, okay, so there are 4 levels of percentage level. So for each level, so we will plot the residual versus the run. So this is the first run, second run, third and fourth run. So we can see also here the range, which is the highest point or highest value of residual and the lowest value of the residual. So we can see the range is approximately equal. So if the range are approximately identical, so we can conclude that the variance is constant. So in summary, we can say that if all the assumptions have been fulfilled, so we can rely on the ANOVA result. If not, maybe we can do something on the data. Okay, for example, we transform the data. Okay, and then we can also do the randomized test. Okay, so then we can overcome the problem that it doesn't meet the assumption of the residual. Okay, that's all for DOE, and also we already cover all the topic and chapters in this course. Okay, if you need any topic to be discussed, okay, so just inform me in the group, so then we can decide whether maybe we can do a Google Meet class. Okay, all the best. Bye. Assalamualaikum.